When we first met the inverse function, it may have occurred to us that we've encountered this word inverse in mathematics before, when we were talking about addition and multiplication. Recall that both addition and multiplication have an inverse property. Every real number A has an additive inverse that we end up finding just by taking its opposite, such that if we add a number to its additive inverse, we get 0. And recall, 0 was the additive identity. So this property tells us that every number has an additive inverse that brings us back to 0. Same deal for multiplication, right? So every non-zero real number, 0 is not included here, every non-zero real number has a multiplicative inverse that we end up finding by taking the reciprocal, such that if we multiply a number with its multiplicative inverse, we get 1 back. And recall that 1 was the multiplicative identity, so there's something we can multiply by to come back to the multiplicative identity. Right, now 0 was the odd one out, because 0 is kind of badly behaved with multiplication, right? Anything times 0 gives us 0. So there's no way we can come back from that. There's going to be a similar restriction on the inverses of functions. And if you think back to what we said about the inverses of functions, you're going to know what it was. Every one-to-one function has an inverse, such that when we compose the function with its inverse, we get the identity back. And this inverse function is the same inverse function that we came up with by exchanging the x and the y in the relation. So this is not some new notion of an inverse function that we're seeing here. This is just another way of looking at the inverse function, and a way of understanding the inverse function relative to this operation of composition. Now, I'm not going to prove that this is the same inverse function. I'm just going to demonstrate it in a specific example. So I'm going to take my function f to be 2/3 x plus 4. To find its inverse, right, I make that exchange the x and y move, and I get x is 2/3 y plus 4. Now I solve for y. First I subtract 4 from both sides. And now I need to get rid of this 2/3. I'm going to choose to think of this move as multiplying both sides by 3/2. And I'll get, after distributing, 3/2 x minus 6 is y. My inverse function is 3/2 x minus 6. What this fact we just stated claims is, if I take f composed with f inverse, that should just be the identity function. In other words, if I take f composed with f inverse, I should just get x back. Let's see. So f of f inverse of x, that'll be f of 3/2 x minus 6. So that'll be 2/3 times 3/2 x minus 6 plus 4, because that's what f does. All right, we distribute, and we get 2/3 times 3/2 is just 1, so we have x. 2/3 times 6 is 4, so we have x minus 4 plus 4. Minus 4 plus 4 cancels out. We're just left with x. Furthermore, our property here says that if we compose the other way, if we take f inverse composed with f of x, we should also get the identity at x, or just x. I'm going to have you try this one. Find the expression for f inverse composed with f of x, and confirm that you do indeed get just x back. Pause the video and try this now. Okay, so we take f inverse of f of x, so that'll be f inverse of 2/3 x plus 4, which should be 3/2 of our input, 2/3 x plus 4, minus 6. Simplifying this, first we'll distribute. 3/2 times 2/3 is just 1, so that's just x. 3/2 times 4 is 6, so we'll have x plus 6 minus 6, which is indeed x. Okay, that's actually pretty neat. And that also comes back to something that we saw in a previous lesson. Previously we noticed that if we have an equation of the form f of x equals a number, where f is a one-to-one function and c is a number in its range, then the solution could be found by just applying the inverse function to that number. So we did a number of exercises of that form, where you were given the inverse function and asked to use it to find solutions. At the time, we understood that as just interchanging the x and the y, right? Just interchanging the argument and the result. But there's another perspective here. We have this sense that we can do the same thing to both sides of an equation, right, and get an equivalent equation with the same solutions. Our basic repertoire of same things, well, we can add a number, or of course subtract, because subtraction is just addition in disguise. We can also multiply by a number that is not 0. But in fact, we can add a third thing to that repertoire. We can in fact apply any one-to-one function to both sides of the equation, provided, of course, that the expressions on either side are actually representing numbers in the domain. Interestingly, remember that the numbers that are not 0 are the ones that had a multiplicative inverse, and the one-to-one functions were the ones that had an inverse as functions. It's not a coincidence that these are the things that we can apply without changing the solutions. Throughout this course, we're going to encounter situations where we do a same thing, yet oddness occurs in our solving process. No oddness occurs if we multiply by a number that is not 0. No oddness occurs if we apply a one-to-one function with an appropriate domain. So another way that we can think of this move is as applying f inverse to both sides of the equation. So then we would have f inverse of f of x is f inverse of c. And since f inverse of f of x means f inverse composed with f of x, that just gives us x back. And so we're left with x equals f inverse of c. We're going to continue to think of that move as just exchanging the x and the c, just exchanging the result and the argument. But this is another perspective on that move. And this will become, again, more useful as we have more complicated functions. We don't need this as long as our functions are linear, because these first two moves will suffice as long as the functions are linear. But as we move into solving equations involving nonlinear expressions, we'll want to keep this in mind, and we'll want to be alert for the one-to-one functions.